final talk for this session is Mike Dodds from Galois. And then it's coffee.
Sure thing. Here you go. Okay, great. Hi. So a bit of context on me. From 2004 to 2017, I was an academic. I was in an office next to Peter. I was also in an office next to Matt. So this is the sort of join or bottom of some lattice, I think. I did a lot of work on separation logic and concurrency and also some weak memory. And since 2017, I've been a principal scientist at Galois, working on a not totally disjoint set of things: formal methods, parser security, cryptography verification. And Galois, I think this is a bit relevant. It's a contract research shop. We do research by the hour. You pay us, we do research for you. And we mostly do security and reliability technologies, things like PL, formal methods, static analysis. And we do a lot of stuff for DARPA, US government. So the caricature prototype Galois project is that you all have written some PLDI papers. We take those PLDI papers, build prototypes, do further research, push it a bit further down the transition path, and then we find out what works in practice, because it's very hard to tell from just reading your wonderful PLDI papers or POPL papers or whatever. The other thing I wanted to say is, hello from the peanut gallery, because my last weak memory paper was written in about 2017-18, and I follow the literature like a bit, and I enjoy all of your papers. But this is definitely not like an area that I'm deeply, deeply in. That also will become relevant as I finish the rest of this talk. And this talk is supposed to be a bit polemical, so confidence low, but maybe useful to say it. So hopefully it's useful. Here's a true story. I go and talk to somebody, and you can imagine this is a potential funder or someone who's kind of a potential client, someone we care about who cares about security and reliability. I say, weak memory is very interesting. Memory systems have these non-SC behaviors. I'm channeling Peter or Mark or someone like that. We have these kind of unsolved theories. We don't know how to define the theory of these things. We don't have the models. The models are often don't match the empirically defined behavior. And the testing and tools we have don't take these effects into account. So we should build new theories and models and tools. And then the person I'm talking to says, okay, but how do we know that weak memory matters? Okay. Well, this was a surprise someone said the first time someone said it to me, because I didn't think of things this way. And I have to back up a bit and think, well, what does that mean? Well, when we're talking to Galois clients, Galois clients want tools to solve problems. And they have lots of problems. It turns out the software kind of sucks. There's lots and lots of things out there that are big, big problems. They really like formal methods. Formal methods are good tools for solving these problems often. But they want to prioritize based on what matters to them. What matters to them is not absolute value in the world. What matters to them is based on the current sort of system, the threat models, the current team, all sorts of other things, the language it's written in, where the current state of the system is. And so it's hard to say for every single client, every single target. But more or less, people care about these kinds of things. They care about system-level impact for a particular problem. So a phenomenon we're examining generates security and reliability issues pervasively or for important classes of systems or users. Security relevance, this is a huge one for kind of the people we work with on the US government. Like, it generates serious security problems. Expert teams can't solve these security problems, even given the tools they have at the moment. An inadequate existing practice. So even if we try really hard, even if we use our existing tools, they don't mitigate the problems. The problems are kind of big problems for them, even if we kind of try and fix them. And maybe we can mitigate them, but it's very, very expensive. Okay, so this is a security-centric and system-centric view of the world. And this is not the only view that's available. I'm not standing here saying, like, you're wrong and I'm right. I'm just saying this is a view that I encounter an awful lot when I'm talking to people. So lots of formal methods domains matter in the sort of, I'm using the word matter here, but you should sort of put a little asterisk next to it every time I say it. Lots of potential formal method target domains matter in this sense. So memory safety is the really famous one. So Microsoft, thank you very much, Microsoft. Thank you, Microsoft. They put out this blog post where they very helpfully said 70% of our CVEs are memory safety issues. And then we were like, thank you very much. And we then told everyone to write everything in Rust. Great. That's really useful for us. It's really useful in like understanding the shape of the kind of reliability problems that people are facing. Parser security. I'm sure a lot of you have seen the recent Kaspersky blog post about this unbelievable operation triangulation exploit chain. I strongly recommend you look it up. It's really one of the most sophisticated attacks in history. What's that? Oh, yeah, the talk is great. There's also this lovely psychic paper attack in parser security where two Apple iMessage parsers are individually correct, but because they parse things differently, that's an attack. Mind blown. Very cool. And also, even a bit closer to home, we have microarchitectural timing attacks, things like Meltdown and Spectre and many, many other things, which it turns out can break security models. And intuitively, according to this criteria, weak memory effects should matter. And the reason is because, well, all these things, like it's intimately related to the semantics of memory, related to memory safety issues. There's a subtle semantics for many unexpected behaviors. So it's hard for experts to get it right. The code runs at high privilege in the kernel, typically. The model can break language-level abstractions. And we've even got a close family resemblance to microarchitectural timing attacks that have similar causes. And so now, if we think about this hypothesis that weak memory matters in this sense, how does it really stack up? What does our evidence look like? Well, the first thing is system-level or user-level impact. Well, I'm sure that there are crashes caused by weak memory effects, but do we have like real examples of system-level reliability or security issues that are caused by weak memory effects? What are they? Can we point to them? Well, I mean, I don't think that I have the kind of things to point to for that. Are they rare? Are they common? How are they mitigated at the moment? Matt said, well, they just do an awful lot of testing. Well, okay, they're doing a lot of testing. That seems to work. My iPhone works okay, and that's got weak memory effects in, as does every single device we use. Security relevance. Are there examples of security vulnerabilities or exploits that arise from weak memory? Are they pervasive? Are they important? Are they hard to eliminate? Well, I found one CVE when I went out looking for it. It was filed by the Rust Belt project. Thank you, the Rust Belt project. But it's not like an attack that's actually out there being used in practice. Are there inadequate existing practices? Well, a lot of you all are practitioners, and that's great, but I don't have a real sense or like a lot of evidence that, in fact, you're struggling to build the systems you want to build. Would it be really nice to have what models would solve these problems? Yeah, it would, but I don't know that it's kind of like difficult. Paul's about to contradict me, so thank you, Paul. John, do you want to go over and counter to him? Paul can tell me I'm an idiot. It's
Well, if you want, I can tell you you're an idiot.
Well,
but,
please, bring it on. Bring it on.
What we do is we tend to say, is there a potential for an attack? And if there is, we treat it as such.
Yeah.
My belief is that there are plenty of vectors due to weak memory, but the people doing the attacking get a lot more bang for their buck attacking memory safety issues and other things like that because they have the practice there, and they're easier to attack.
I have a slide which is just for you in about 2 minutes. Okay.
My condolences.
Okay, so I don't feel overall, according to this definition of what matters, that I have very compelling evidence that I can go to my funders, to my clients, and say, look, weak memory is where it's at. We need to kind of do this quick. What are some counter hypotheses? Well, okay, counter hypothesis number one: Mike is dumb. There are weak memory effects do matter in this sense. There's lots of evidence. I just don't know about it. Great. Hello from the peanut gallery. The peanuts are delicious. Thank you. Thank you. Counter hypothesis number two. Okay. Weak memory effects basically never happen. And so what we have here are a big set of behaviors that are allowed by the models. We have a middle-sized set of behaviors that are allowed by the in the lab effects. And we have a teeny tiny set of behaviors that actually occur in production. And that teeny tiny set includes nearly none of the really weird sort of behaviors that we like to kind of like write POPL papers about. And so this means that bugs are kind of caught in testing, or they basically don't happen. But microarchitectural timing attacks do also are also rare and also very hard to correlate, and they cause attacks. So another hypothesis is that weak memory code is very tiny and very encapsulated. And it's mostly core concurrency constructs. So the code is already highly reliable. It's tiny in scope. It's heavily audited. It's written by super, super experts, hell out there in the audience. The code's often co-designed with the models. So the designers of the code are working with the model designers to make sure the model and the code are doing compatible things. And the code is also deeply encapsulated in the system. So it's in schedulers, it's kind of locks, right? You know, as compared to like a crypto library is very smart, written by very smart people. It's very heavily audited, but it takes untrusted inputs. A scheduler doesn't really take untrusted inputs in that sense. It's just hard to kind of attack it in that way. Another hypothesis which came up when I gave my practice talk is weak memory developers are just extremely careful, and there's way, way too many barriers in the code. And then on the other hand, maybe there are just like a lot of crashes out there, and we just can't tell. So like someone who works on BSD said, hey, you know what? Things crash all the time. We just don't know that they're weak memory crashes. Because like, how do you reproduce that? You can't. But how would we establish either of these things are true? You know, could we build tools? Are they actually a problem? And how does this mean that weak memory effects matter from a, you know, the security relevance, system level effects point of view? And you know, who are these developers? What is the impact at the system or user level? And like, this is maybe my most spicy, you know, it's not really a hypothesis, but like, is there some reason why these weak memory bugs are not dangerous in some sense? Like a dangerous bug is like a security failure, or the adversary can write to memory. And weak memory bugs are like very rare mystery crashes, or very rare memory corruption. Is there a reason that doesn't matter, that we don't have to worry about it? But is this even plausible? Is there some reason why we would think that that weak memory bugs are like not dangerous? What are typical bug or vulnerability patterns caused by weak memory effects? Those would be very interesting to know. So could we refute some of these counter-hypotheses? I don't strongly believe any of the counter-hypotheses either, aside from my being dumb, which is well established. So are there any other explanations here? I'm sure there are plenty of other things that could be going on. So I'm going to wrap this up on what matters. Galwa clients really like formal methods. They really like modeling, but they have limited budgets. I mean, everyone has a limited budget in time, engineers, you know, learning new tools, all these kinds of things. And they have lots and lots of problems. And so this means picking problems with evidence that they actually matter. And that means security level or user level impacts. That means security relevance. It means inadequate existing practices. And I personally don't feel that I have the evidence from the weak memory world that the weak memory effects matter in this sense. Now, that's not to say that it's not worth working on these kind of problems, but it would be very, very helpful for me personally in my job to be able to sort of point to this, something that says, look at this. 70% of blah is blah, you know, or sort of like, look at this thing over here. You know, that is very useful, and it also helps to kind of expand the community, as we've seen with the microarchitectural timing attacks. Once you have that kind of evidence, that can be a real motor for building new tools, doing new research, expanding the community. I want to finish off with, you know, a provocative suggestion. Here's my modest proposal. Stop building models, start building exploits. So if we want evidence that weak memory matters, we should build the evidence that weak memory matters, and that means becoming vulnerability researchers. And so I think that my hypothesis is kind of the same as Paul's, really. There's actually a lot of these effects should matter and probably do matter, and that there is an underexplored space of weak memory security research. And what that means is building system-level CVEs, exploits, and case studies that result from weak memory effects. We have all these amazing models. We know all these kind of weird behaviors. Matt's been saying that the kind of code does like all sorts of exotic things, many which we don't even know how to account for in the models that already exist. And then we take them and we write white papers and go to DEF CON or Black Hat or Oakland and say, hey, look at this. I broke this kind of like security guarantee. I built this exploit chain. And then, so there are a couple of topics in security which anyone out here who's like a PhD student who's excited about a new field that would be good to look into. Like secure compilation is very related to this. If you haven't looked into things like return-oriented programming and weird machines, those also seem very related. Microarchitectural timing attacks I mentioned are there. They're also very related. So I think that there's a rich space here potentially to go out and kind of go fishing for these kinds of exploits. Maybe. Well, that's all I had to say. Thank you very much.
I can give you one anecdote in favor of your over-synchronization thing. One of the good things in the last few years, I've actually got some people that are studying my code and learning it, in case Mother Nature forces me into a retirement program soon. And they found a place, it wasn't on a fast path, where it was over-synchronized. But we left it because if you removed any of the memory barriers that formal analysis showed you removed, it became very difficult to explain how it worked.
Yeah, and it's sort of interesting to think, so let's imagine we kick out all the memory barriers we think we kick out. Well, what do we expect to be the performance improvement? If it's 5%, well, maybe, that's not like a big deal. But maybe if it's like 500%, that's a big deal.
For 5%. 5%
Well, okay. 5% of what is the kind of key? Yeah.
5%.
Yeah.
So its source of weak memory exploits that might be worth looking into is the JVM. So applets in the browser are not really a normal deployment model for Java anymore, but at least it's a design goal that you should be able to run completely untrusted code that you got off the internet in the JVM, and it should be sandboxed by JVM mechanisms. Those sandboxing mechanisms rely on type safety. If you can get two pointers to the same memory that disagree on what type they are in JVM bytecode, then you can break everything. And Java code has free access to threads and can observe weak memory effects. So the Java VM has to ensure that weak memory effects don't allow untrusted code to confuse types. Otherwise, you get an exploit fairly easily.
Yeah, and I think that I know that there's been a couple of papers. I think one of Victor's papers pointed out that you can use kind of some of these weak memory effects to kind of break like type guarantees. And so that's the place where, if I was going out looking for exploits, you're exactly right. That's where I would look at kind of like breaking the security model and then trying to kind of build exploits. And I think you're right that JavaScript is another place where kind of you've got, that's where some of the Meltdown and Spectre attacks were kind of via JavaScript injection. So I think the browser is a great place to go looking for those kind of things.
Cool. So I have two comments in support of your slides. So the first one is, so that 70% number you talked about that Microsoft produced, when they generate that data, there is basically a security researcher for everything that gets submitted, and they have to reproduce it and demonstrate that it does exactly what's said, and then the person gets a finder's fee. And it's going to be really hard to reproduce the sort of weak memory effects, right? So they probably will go into some bucket of not properly categorized or not reproducible or something, so it's not going to end up in a nice, easy statistic. And your conjecture about using vulnerabilities to influence what people do is a big strategy inside Microsoft security teams for getting people to do things. They will literally send a VNR researcher after that product and go, no, it's broken here, 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 here. You have to either do what we say or fix all these things in your existing code. And they move them that way.
Yeah. And I think that the CVEs are like, there's actually amazing lever for moving the world. It's even like in open source as well. Yeah, Hans.
Yeah, security is of course very important, and vulnerabilities are very important. On the other hand, I'm sort of with what everybody else is saying here. With that, it's very hard to exploit these concurrency issues very often anyway. On the other hand, there's another issue here. I mean, what we see, and I think most other people I've talked to have similar problems. That especially for code base written in C++ or something like that, we see sort of this background level of bugs that are really annoying to deal with because they're impossible to track down.
Yeah.
And that's where a lot of time goes. And I don't know how many of those are actually caused by weak memory issues, but I suspect it's not negligible, but I don't really know. So I think that's another possibly more hopeful way to justify this.
Yeah, and I think that if we had some data that like, I mean, I don't dispute that hypothesis. I think that that's very plausible, but it would be great to have like system level tools. I mean, it's a very, very hard problem, of course, because like tracing all the way from like, database fell over to kind of like, there's some sort of reordering in the kernel. But I think that in order to kind of justify that this, it'd be really great to kind of like know, like for sure that this was caused by this, that would be very helpful. I mean, I think that maybe another related thing is I think that some of the systematic concurrency testing, which I know that Matt has been somewhat involved with, is like the kind of Coyote thing that Microsoft built, which is about kind of basically controlling the scheduling and trying to kind of show that you can demonstrate bugs. It's sort of potentially kind of interesting in this regard, because you could use it, if you could find a way to do it, maybe you could find a way to reproduce these Heisenbugs that just appear one time, your database crashes, you're like, well, what the hell happened? And then never appears again. Well, maybe we need some sort of systematic way to kind of do that testing, and then we can find out what's actually really going on.
Yeah.
That'd be great.
Yeah. Yeah, I mean, I just wanted to mention the other part of memory model issues here is the compiler side, right? When you talk about programming languages, memory models, part of that is basically rules about compilers, and certainly there are violations of programming language model memory rules that break things reliably, and we have, I think, a fair number of instances of that. But that's a different issue from the hardware one.
Yeah, but are those like exploitable, or are they just kind of what do they? I mean, my question is going to sort of be like one step further down the chain there, which is
actually,
like,
I'm not sure
this sort of so what question, I suppose.
Yeah, I'm not sure whether I've seen exploitable ones. I suspect those exist actually, because the sort of a standard example in Java is forgetting to declare something volatile, and then having it optimized out of a loop. I would be surprised if that hasn't resulted in a vulnerability somewhere. But
yeah, I mean, that would be really cool to have that kind of captured somewhere. The sort of zoo of weak memory effects, sort of bad things. That would be great.
Okay. Final question from Enan.
I see you have a point in the last slide about what the community lack is hackers. We need more hackers, because I spent some time a couple of years ago taking a look to this Spectre thing, and where I heard that security people, even before Spectre became a thing in 2018, they knew for quite a long time that speculative execution was a surface attack. But it was not until they managed to actually consistently reproduce or come up with the attack that this became a thing. So I think that in memory, weak memory maybe has the same thing. So there might be a surface attack in there, but it's just that we don't know yet how to exploit that.
Yeah, it's there's a journal, it's not very serious, it's called proof of concept or get the F out, and I think that that's like an attitude that these kind of people have. But I think there are a lot of papers about sort of, well, this might be dangerous. Well, until you can show like a proof of concept, then people don't really take you seriously, is my impression.
This is exactly the kind of thing you said at the beginning that Galway does. We write a couple of PLDR papers, this is eventually it can be done.
Well, as I mentioned, I have tried. So yes, I also would like to do this. Yeah.
Thank you very much, Mike.
Thanks.